Welcome to the deep dive. We're here to plunge into some complex topics and, well, get you up to speed quickly and effectively. Today, we're taking a journey into a really critical, but honestly often overlooked part of network communication. That's OSI Layer 6, the presentation layer. Our mission for this deep dive is simple: get you thoroughly informed about incident response, playbooks, runbooks, all tailored specifically for this unique layer. It's unique, but as we'll see, increasingly vulnerable in today's architectures. We'll be focusing on layer six's job, things like encryption, compression, how data gets serialized and encoded, and the kind of surprising security issues that pop up because of these functions. Our insights today, they're drawn from quite a bit of research, established frameworks, think NIST, ISO 27035, SANS, and also some really compelling real-world cybersecurity incident analysis.
Yeah, and what's really fascinating here, I think, beyond just the dry technical terms, is how this layer, which seems quite abstract, right, it really functions as the internet's universal translator. It's kind of the hidden gear ensuring data makes sense across different systems. But that very function, handling translation and formatting, that's what makes it, well, an increasingly attractive target for attackers who know what they're doing. You find a lot of organizations, even with strong defenses elsewhere, they're just not quite ready for the, let's say, nuanced attacks that operate right here at Layer 6. Understanding this dynamic is, frankly, strategically vital if you want to build a security posture that's truly resilient.
The universal translator. I like that. It really paints a picture. Okay, so for anyone needing a quick refresher, or maybe you're newer to the networking world, let's just quickly unpack the OSI model. OSI stands for Open Systems Interconnection. It's basically this foundational framework, a conceptual model, that splits network communication into 7 distinct layers. Each layer has its own specific job, handling everything from the physical wires, layer 1, all the way up to the software you interact with at layer 7. And layer 6, the presentation layer, our focus today, it's nestled right there, kind of in the upper middle section. It sits just below the application layer at layer 7 and right above the session layer at layer 5. I sometimes think of it like a data diplomat. Its job is ensuring that whatever data arrives, no matter its original format or where it came from, it gets presented in a way the receiving application can actually understand and use. It's this essential go-between that makes communication across different platforms, well, possible.
That data diplomat analogy is actually pretty good. It captures the essence well. Its core jobs are, when we think about it, quite fundamental. We're talking data format translation, handling compression to make things efficient, and then the really critical functions, encryption and decryption. Think about it like this. When data starts at an application, maybe you're typing an email in your client at layer 7. It doesn't just zap straight onto the network. No, first it goes down to layer 6. And at this stage, the presentation layer takes that raw data and meticulously prepares it, formatting it correctly, maybe compressing it so it travels faster, and crucially, encrypting it if needed for confidentiality. So when you hit send, layer 6 is doing a whole lot of work behind the curtain, getting that data ready and secure before it even leaves your device. And then conversely, when data comes in from the network, layer 6 gets it from layer 5, the session layer. It then just reverses the whole process, decrypts it if necessary, decompresses it, and translates it into a format that the application waiting at layer 7 can actually read and process. It's this constant two-way translation service that makes layer 6 so vital. Now, the security angle is so what here? It's this tight relationship between layer 6 and layer 7. It means any problem, any compromise at layer 6 directly impacts the data that gets shown to the user or processed by the application. An attack here isn't just some minor glitch. It can subtly corrupt data, maybe manipulate character encoding or break the encryption. Ultimately, it could present a malformed or even actively malicious payload straight to an application that just isn't expecting it, isn't built to handle that kind of subversion. This really highlights just how critical Layer 6 security is. Its functions are directly responsible for the security, the integrity, and frankly, the usability of the data applications rely on. If this invisible translator gets corrupted, well, everything downstream is potentially compromised too.
That really clarifies its importance. And it explains something else, too, why these layer 6 attacks can be, well, sneakier, more dangerous, maybe, because they're harder to spot. We hear all the time about layer 7 attacks, right? SQL injection, cross-site scripting, or layer 3 network attacks like DDoS. Those usually make a lot of noise, trigger obvious alerts. But layer 6 threats, it feels like they operate in a different space, much more subtle. It's about the data representation, isn't it? Not just raw traffic floods or obvious bugs in application logic. It feels like a shift towards, I don't know, machine deception, tricking systems into misinterpreting the data structure or syntax, bypassing the usual security controls we focus on. It's like attacking the very foundation of trust between systems.
You've absolutely nailed the core challenge there. These attacks aren't always about finding a simple bug or a known malware signature. They're about manipulating the language data uses. To really get a handle on this stealthy threat landscape, let's maybe walk through some key presentation layer protocols and where they're vulnerable. Okay, first up, the big one. SS, LTLS, secure sockets layer, transport layer security. These are the workhorses, right? Encrypting our web traffic, APIs, tons of stuff. But they're not perfect. They can be vulnerable to downgrade attacks, forcing a connection back to an older, weaker version, or specific cipher exploits. And we've seen sophisticated attacks too, like key reinstallation attacks, the KRACK attack being a prime example.
KRACK, right? That affected Wi-Fi encryption.
Exactly, a classic Layer 6 issue. Then you've got the fundamental ways we represent characters. ASCII, EBCDIC, Unicode. These define how text is encoded. Attackers can exploit character encoding manipulation, or even use things like Unicode homoglyph attacks, using characters that look identical to a human but are different to a computer, maybe to spoof a domain name or bypass a filter. It's like a digital forgery.
Sneaky.
Very. Then for data representation and compression, think about common file formats. JPEG, MPEG, GIF. These can be vectors for malicious file formats, talk about compression bombs later, or metadata manipulation, hiding bad stuff inside the file's extra info. gzip, used specifically for compression, has its own vulnerabilities too. Can be used in compression attacks or for denial of service. And lastly, maybe less commonly known but important, is ASN.1 Abstract Syntax Notation 1. It's used a lot in telecom and network protocols for defining data structures. And guess what? It can be exploited through malformed data or parsing vulnerabilities. Each of these, they serve a vital function, but each also presents this often overlooked attack surface right at Layer 6.
That's a really thorough list, and it drives home just how deeply these L6 functions are embedded in everything we do online. So if those are the components, how do attackers actually exploit the format and syntax? You mentioned format string attacks earlier. What's clever about them? And maybe what's the most counterintuitive part about defending against them?
Good question, because the counterintuitive part is often what trips people up. A format string attack is, well, it's a classic example of messing with data syntax at Layer 6. It happens when a program, usually written something like C or C++ EB, incorrectly takes input provided by a user and treats it as a formatting command instead of just plain data. Think of functions like print or sprintf. If a developer isn't careful and maybe writes code like printf user input, where that user input comes straight from outside without proper checks. Trouble.
Okay, so the program expects data but gets an instruction instead.
Precisely. The attacker crafts their input using special format specifiers. Things like %x to read memory and hex, % to read strings, or even %pro, which is really dangerous because it writes to memory. When the vulnerable print function sees these specifiers, it expects corresponding arguments that aren't there. So instead, it starts reading from or writing to the program's memory stack. This lets the attacker potentially read sensitive data keys, passwords, whatever's in memory, or just crash the program for a denial of service. In the worst case, using %, they can overwrite things like return addresses on the stack and potentially achieve arbitrary code execution. Yeah. The core issue, the counterintuitive bit, is this broken assumption. The program thinks input is just data, but the attacker makes it interpret the input as a command. It's pure Layer 6 attacking the syntax processing. And the best fix. It isn't just trying to filter out % or % after the fact, though that helps. It's fixing the root programming flaw, making sure user input is always treated as data. Like using print %, user input, this % explicitly tells it, treat this as a string no matter what's inside. It's a subtle shift, but fundamental for developers.
That makes total sense. Be explicit about intent. Treat data as data. Okay, shifting slightly, you also mentioned input data and character encoding manipulation. With the internet being global, so many languages, character sets, I can immediately see this being a huge can of worms. What's maybe the most common mistake security teams make when trying to defend against these encoding attacks?
Yeah, it's definitely a complex area. And the most common mistake, probably thinking that simple blacklist filtering, just blocking known bad strings, is enough. It rarely is. The global nature of the internet, with Unicode supporting thousands of characters, creates this massive surface for encoding attacks. Attackers exploit flaws in how applications decode and interpret these character sets. They can craft input, maybe a URL or form data, using an encoded sequence that represents a malicious string.
So the filter doesn't see the bad string directly.
Exactly. A classic example is path traversal. An attacker wants to use JPEG to go up a directory level and access files they shouldn't. A simple filter might block the literal dot string, but the attacker can encode it using, say, Unicode representations like C/C0A per C0A E per C0AF. When this encoded data hits the web server, the presentation layer dutifully decodes it back to line, and boom, the filter's bypassed, and the attack potentially succeeds.
Ah, okay. The filter sees the encoded version, which looks harmless, but the application sees the decoded malicious version.
You got it. The filter designed for one specific representation is blind to equivalent representations in other encodings. It's an attack on the process of interpretation, not just the value. Defending against this means moving beyond simple string matching. You need what's called a canonicalization approach. Basically, you normalize all input into a single, standard, safe format before any security checks or application processing happens. This way, no matter how the attacker encodes it, it gets reduced to its simplest canonical form, which your defenses can then reliably identify and block. The mistake is thinking you can block every possible variation. The reality is you need to enforce one single safe format.
Like a digital chameleon changing its colors.
Yeah.
Very clever. Okay, let's move on to cryptographic and compression attacks. Layer 6 is home to protocols like TL, SSSL. What's the biggest oversight you see organizations make when implementing encryption?
The biggest oversight, hands down, is often complacency. Relying on outdated protocols or weak configurations, maybe thinking, well, at least it's encrypted. That's just not good enough anymore. Layer 6 handles SSL/TLS, the backbone of secure communication online. But their security really depends on using strong versions and secure configurations. Attackers can exploit weaknesses here. A common method is a man-in-the-middle or MIOM attack. The attacker gets between the client and server during the connection setup. They can then try to force a protocol downgrade. They trick the client and server into negotiating down to an older, less secure version of TLS, maybe even TLS 1.0, or worse, plain unencrypted HTTP. A classic example is SSL stripping, where the attacker intercepts an HTTPS request, talks HTTPS to the server, but presents plain HTTP back to the user. The user sees the padlock disappear, maybe, but might not realize their connection is now exposed.
And the user might not even notice.
Often they don't, or they click through warnings. Beyond downgrades, there are specific flaws in the protocols or their implementations. We mentioned KRACK earlier. That exploited a logic flaw in the WPA2 handshake, forcing the reuse of a cryptographic nonce. A nonce is supposed to be a number used once to prevent certain attacks. Reusing it broke the encryption, allowing decryption and even packet injection on Wi-Fi networks. The lesson is crystal clear. Encryption is only as strong as its weakest link. Complexity and the need for backward compatibility can introduce these subtle but serious flaws.
So what's the robust defense look like then?
It means being rigorous. You absolutely must disable obsolete protocols, SSL 3.0, TLS 1.0, TLS 1.1. They're broken. Don't use them. Enforce modern cipher suites, preferably those offering perfect forward secrecy. That means even if a long-term key is compromised later, past sessions remain secure. And of course, patch your cryptographic libraries, OpenSSL, LibreSSL, whatever you use religiously. Keep them up to date. The oversight is thinking encryption is a set-it-and-forget-it thing. It requires constant attention and maintenance.
Right, continuous vigilance. Now, another core L6 function is compression. You mentioned data bombing or zip bombs. That sounds pretty dramatic. Does that kind of thing actually catch organizations off guard?
Oh, absolutely it can. And yes, it often catches them off guard because the threat is sort of hiding in plain sight within a seemingly normal process. Compression is great, right?
Yeah.
Reduces data size, saves bandwidth. It's a key layer 6 function for efficiency. But attackers can weaponize it. A compression bomb, or zip bomb, is a malicious archive file. It looks small, maybe just a few kilobytes. But it's crafted in such a way that when a system tries to decompress it, the process consumes a ridiculous amount of resources. CPU time, memory, disk space. Imagine a 10 KB file that expands to terabytes of garbage data. It can easily overwhelm and crash the system attempting to open it. A denial of service achieved through data representation.
A digital landmine, as you said. How do you spot something like that?
That's where forensics gets interesting. One key insight is that malicious files using heavy compression or encryption often show a high entropy value. Entropy is a measure of randomness or unpredictability in data. Highly compressed or encrypted data looks very random, so does high entropy. Attackers often use packing or custom encryption to hide their malicious code, which also results in high entropy. So analyzing a file's entropy can be a strong indicator that something fishy is going on, even if traditional antivirus signatures don't flag it. This shifts the defensive game. You're not just looking for known bad patterns. You're looking at the inherent properties of the data itself. So yes, it catches people off guard if they only rely on signature matching. Proactive control means using secure, well-vetted compression libraries and keeping that software updated.
Okay, so we've seen how Layer 6 can be attacked through format strings, encoding, crypto weaknesses, compression bombs. What does this all mean for incident response? It feels like traditional methods, maybe focused on network logs or application errors, might completely miss the mark here. What's the biggest hurdle in just identifying that an incident is actually a Layer 6 attack versus, say, just a weird bug?
That ambiguity is precisely the biggest challenge. Layer 6 attacks often masquerade as something else. A system crashes. Is it a bug in the application? A resource exhaustion issue? Or was it triggered by a malformed file exploiting a Layer 6 parsing vulnerability? Data looks corrupted. Was it a transmission error? A database problem? Or did a TLS downgrade allow an attacker to subtly modify it? This inherent uncertainty means you need a specialized approach. Comparing it to other layers helps clarify why. Network layer, L3 attacks like DDoS or IP spoofing usually show up pretty clearly in network traffic metrics. Huge volumes of packets, weird routing, the indicators are often network-centric.
Right, you see the flood.
Exactly. Application layer L7 attacks like SQL injection or XSS typically leave traces in application logs. You see the malicious SQL query, the suspicious script tag. The focus is on what the application did with the input.
Makes sense.
But presentation layer L6 attacks, they're slipperier. They subvert the data itself, its structure, its encoding, its encryption. The forensic indicators are different. You might look for unexpected process crashes linked to specific data inputs, or weird TLS negotiation patterns in packet captures. Or, as we discussed, files with abnormally high entropy. It requires looking deeper than just network flows or application error messages. You have to analyze how the data is being presented and interpreted. It's a different kind of detective work, needing a specific L6 lens.
A digital linguist, like you said. Okay, so if our standard IR plans aren't quite enough, how do we adapt frameworks like NIST, ISO 27035, or SANS for these L6 threats? What's the main mental shift needed for an incident response team when they suspect a Layer 6 compromise?
That's the key question. Generic plans provide a good skeleton, but they lack the specific muscle needed for L6. Frameworks like NIST's Incident Response Lifecycle, preparation, detection analysis, containment, eradication, recovery, post-incident activity are excellent guides, but each phase needs that L6 tailoring. The biggest mental shift for responders. It's moving beyond just asking what system broke to asking how was the data representation manipulated or misinterpreted. Let's walk through the phases with that L6 focus. Preparation. This isn't just about having a plan on the shelf. For L6, it means strong, secure coding policies before code is written. Secure defaults for TLS configurations. Up-to-date threat intelligence, specifically on L6 vectors, like new encoding tricks or crypto flaws. It's proactive defense baked in.
Building resilience beforehand.
It's exactly. Detection and analysis. This is where the mental shift is critical. Don't just look for firewall pings or AV alerts. Look for subtle anomalies. Those application crashes with weird stack traces pointing to data handling, failed certificate validations, network alerts on high entropy files being downloaded. Your CM and IDEPSIS are vital, but they need rules and analytics tuned to spot these L6 specific indicators, correlating data across layers.
Got it. More nuanced detection.
Containment. Okay, you suspect an L6 issue. Containment might mean isolating the host, yes, but also potentially disabling a specific vulnerable protocol, like an old TLS version, across servers. Or blocking IPs sending malformed data. It's about stopping the data manipulation pathway. Eradication. This isn't just deleting malware. For L6, it means finding the root cause, identifying the exact line of code vulnerable to the format string attack, patching the specific crypto library flaw. Removing all instances of the malicious compressed file, it requires deeper technical analysis.
Fixing the core representation issue.
Precisely. Recovery. Restore from clean backups, yes. But after applying the necessary patches identified during eradication, then rigorously test, can you still force that TLS downgrade? Does the app still crash with that weird file? Validate the fix. And finally, lessons learned, post-incident activity. Document everything. What L6 indicators did we initially miss? How effective was our runbook for that ASM.1 parsing attack? Update playbooks, runbooks, and crucially, developer training based on these findings. The shift is always back to how was the data's presentation layer exploited, and how do we prevent that specific mechanism next time? That's a really practical breakdown. So the framework guides the overall response, but you mentioned playbooks provide the specific blueprint for types of incidents. What does a Layer 6 focused playbook actually contain? How does it help ensure everyone from tech teams to legal is on the same page for these tricky incidents? Right, the playbook is that strategic high-level guide. It standardizes the approach to managing a certain category of incidents, like cryptographic protocol attacks or data representation exploits. Its real power for Layer 6 lies in fostering that cross-functional collaboration you mentioned. These incidents can touch application code, network config, security tools. You need everyone aligned. A good L6 playbook connects IT ops, app dev, SecOps, maybe legal, PR, ensuring everyone understands their role when, say, a subtle encoding attack bypasses filters. It defines the who does what at a strategic level.
So what are the key ingredients of one?
Typically, you'll have objectives and scope. What are we trying to achieve with this playbook? Minimize data exposure from TLS issues, prevent DOS from compression bombs, clear goals guide the response, roles and responsibilities. Critically important, who's the technical lead for analyzing malformed data? Who handles communication if customer data might be impacted? Who liaises with legal for evidence preservation? Assigning roles avoids confusion in a crisis. Incident categorization. How severe is this L6 incident? A minor encoding bypass might be low priority, but a format string leading to RCE is critical. This helps prioritize resources. Communication plan. Who needs to know what, when, and how? Internal teams, leadership, maybe external parties. Having pre-approved message templates helps ensure clear, consistent communication. And finally, response procedures. This outlines the general steps that flow from detection to recovery for this type of L6 incident. These steps are then fleshed out in much more detail in the tactical runbooks. The playbook provides the map that assigns the drivers. The runbooks provide the turn-by-turn directions.
Okay, so playbooks are the strategy, the what and who. Runbooks are the tactics they're the detailed checklists for specific scenarios, right? Can you walk us through a couple of practical examples? What makes a runbook truly actionable for someone on the security team in the middle of an incident?
It's exactly. Runbooks are where the rubber meets the road. They need to be super detailed, step-by-step guides for a specific, known attack pattern. The key to making them actionable is the 5 A's. Actionable, accessible, accurate, authoritative, and adaptable. They need clear steps, easy to find, technically correct, trusted, and updatable. Let's take that format string attack example again, but as a runbook. Runbook 1, format string attack response. Trigger, CM alert for potential format string specifiers, %, in user input fields, or application crash logs pointing to a vulnerable function like print. Step 1, detection analysis, log review. Find the full input string containing the format specifiers. Check application system logs for preceding errors or unusual memory usage. Use EDR/MDR tools to examine the process data crash time. Action. Collect memory dump of the crash process using tools like procdump or OS equivalents. Capture a full forensic image of the host if feasible, using FTK Imager, DD, etc. Document everything meticulously.
Very specific actions and tools.
Yes. Step 2. Containment. Isolate the affected host immediately using NEC or EDR network containment features. If the vulnerable service can be identified, stop or disable it. Block the source IP address identified in logs at the firewall WAF. Block any associated malicious user agent strings if applicable. Tools, NEC, EDR, firewall WAF console. Step 3. Eradication and recovery. Analyze the memory dump using volatility, GDB, and/or source code if available to pinpoint the exact vulnerable line, reasonable, print, user input. Work with developers to remediate using a safe function, UDG print SNIC user input. Deploy the patch code via CI/CD or manual update process. Restore the system service from a known good backup taken before the incident if data corruption occurred. Tools, debuggers, SASTAT tools, version control, backup solution. Step 4, lessons learned. Conduct postmortem. Update secure coding training for developers focusing on input handling. Add checks for format string vulnerabilities to SAS tools in the CI/CD pipeline. Update this runbook with any new findings.
Okay, that's super clear. What about the TLS downgrade?
All right, runbook 2. TLS downgrade attack response. Trigger. IDSF's alert for SSL TLS downgrade attempt. SIAM correlation rule firing on clients connecting with weak ciphers. SSLv3, TLS 1.0, High number of certificate validation errors in server logs. Step 1. Detection and analysis. Use Wireshark or similar packet analyzer on affected server segments or via SpanTap port. Capture TLS handshakes. Action. Filter for TLS traffic, SSL or TLS filter in Wireshark. Examine client hello. Check advertised ciphers versions and server hello. Check selected cipher version. Look for mismatches or selection of known weak options. This confirms the downgrade. Identify source IPs attempting the downgrade if possible.
Analyzing the handshake itself.
Critical here. Step 2. Containment. This is immediate configuration change. Action. Access server load balancer configurations. AG, Apache, Nginx F5. Disable all insecure protocols, SSL v3, TLS 1.0, TLS 1.1, and weak cipher suites, GRC4, DES, low-strength DH. Enforce TLS 1.2 as minimum, preferably TLS 1.3. Apply and test the configuration change. Block identified source IPs at the firewall. Tools. Server will be config files GUIs, firewall console. Step 3. Eradication recovery. Ensure all relevant software, OS, web server, libraries like OpenSSL is fully patched against known TLS vulnerabilities. If certificates could have been compromised, example via Heartbleed-era flaws, revoke and reissue them. Perform vulnerability scans specifically targeting SSL TLS configurations to confirm remediation. Step 4. Lessons learned. Update baseline server hardening standards to mandate secure TLS configurations. Implement regular automated configuration checks. Update this runbook.
Makes sense. And one more, maybe the malicious file format.
Sure. Runbook 3. Malicious file format compression bomb response. Trigger. User reports application crash after opening a specific file. EDR alert on a suspicious file execution write. Network security tool alert on download of a file with abnormally high entropy. Step 1. Detection and analysis. Isolate the user's host immediately. Network containment. Obtain a copy of the suspicious file safely. Do not execute it. Action. Calculate the file's entropy using tools like ENT or features within forensics suites, via Kurt or incident forensics. Analyze the file structure if possible, for example using hex editors, format-specific tools. Detonate the file in an isolated sandbox environment, Cuckoo Sandbox, any run, commercial sandbox, and observe its behavior, network connections, file writes, process creation. Document observed indicators of compromise, IOCs like file hashes, domains contacted.
Sandbox is key there.
Absolutely. Step 2, containment. Quarantine the malicious file hash using EDRV across all endpoints. Block any malicious domains IPs identified during sandbox analysis at the firewall proxy. Scan other hosts for the presence of the malicious file hash. Step 3. Eradication and recovery. Delete all identified instances of the malicious file. Identify the vulnerable application library that mishandled the file format. Requires analysis of the crash sandbox results. Work with vendor or developers to patch the vulnerability. Restore user data from backup if necessary. Step 4. Lessons learned. Reinforce user awareness training about opening attachments downloads. Evaluate security controls for file analysis, sandbox, entropy checks. Update vulnerable software libraries proactively. Update this runbook.
Those are incredibly detailed. It really shows the level of tactical planning needed. And to execute these, you obviously need the right tools in your belt. What's the essential toolkit for L6 incident response? What makes these tools suitable beyond just general security monitoring?
Yeah, having the right tools is fundamental, because L6 incidents often require looking inside the data stream or the file structure, not just observing high-level behavior. First up, packet analyzers. Wireshark is the king here, obviously. It lets you get right down into the weeds of network traffic. For L6, it's indispensable for dissecting TLS handshakes, spotting malformed packets based on protocol specifications, seeing exactly how data is encoded on the wire. You need that granular view.
Seeing the actual presentation data.
Precisely. Then, SIEM and log management platforms. Critical for correlation. A good SIEM pulls logs from everywhere: apps, servers, network gear, security tools. For L6, it's about correlating maybe an application log error with a specific network session showing a weird TLS negotiation, or a file download alert followed by an endpoint crash. That correlation is key to spotting these subtle attacks. Forensic analysis tools. These go beyond standard AV. Think tools like IBM QRadar Incident Forensics, or even command line tools like strings, file, ent. They let you analyze file structures, calculate that crucial entropy value to spot packed or encrypted payloads, extract hidden data. They help you understand the content and structure, which is core L6 territory.
Tools to look inside the data.
Exactly. And don't forget the basics. Encryption and compression software itself needs to be secure. Using robust, up-to-date libraries and tools like modern OpenSSL, 7-zip with updates is a preventative measure. Part of the toolkit is ensuring your own L6 implementations aren't vulnerable. The beyond general aspect is choosing tools known for secure implementation, not just any old library. And looking forward, SOR platform security orchestration, automation, and response. These are becoming vital for handling the volume and speed needed. Imagine automating the process. Alert comes in, SOR pulls the suspicious file, submits to sandbox, checks entropy, maybe even isolates the host or blocks the hash, all before an analyst even logs in. That automation is key for scaling L6 defense.
That toolkit really emphasizes the depth needed. Okay, let's make this even more concrete. Real-world examples often hit home the hardest. Can you share a couple of powerful case studies where Layer 6 vulnerabilities were the core issue?
Absolutely. One of the clearest, almost textbook examples of a pure Layer 6 incident is the KRACK attack we mentioned earlier. Remember, this wasn't an attack on a router, Layer 3, or a web application, Layer 7. It targeted the WPA2 Wi-Fi encryption protocol itself specifically, the four-way handshake used to establish session keys. That handshake process is a Layer 6 function, defining how cryptographic keys are negotiated and presented. The attack involved cleverly manipulating and replaying messages within that handshake. This tricked the client device into reinstalling an already used encryption key. The critical impact was forcing the reuse of a cryptographic nonce, which, as we know, should be unique for each packet with that key. Reusing the nonce fundamentally broke the confidentiality guarantees of the encryption, specifically CTR mode with AES, allowing an attacker on the same Wi-Fi network to decrypt traffic and, in some cases, even forge and eject packets.
And the fix wasn't a firewall rule.
Exactly. The fix required patching the implementation of the WPA2 protocol on end devices, laptops, phones, routers. It was a flaw in the logic of the presentation layer protocol itself. It beautifully illustrates why understanding these layers is crucial for knowing what to patch and how to respond. It was purely about manipulating the cryptographic presentation.
A perfect L6 example. What's another one?
Another compelling area, often seen initially as just malware, is ransomware encryption. Let's take the Xion ransomware as an example, though many operate similarly. While ransomware often arrives via Layer 7, phishing email, malicious website, its core destructive action encrypting files is fundamentally a Layer 6 operation. It's manipulating data representation to make it unusable without a key. Xion, for instance, used a hybrid approach. For each file, it generated a unique symmetric key. Using AES, it used that AES key to encrypt the file's content. But then, to protect the AES key itself, it encrypted that key using an asymmetric algorithm, RSA, with a public key embedded in the ransomware. This encrypted AES key was then appended to the encrypted file. From an incident response and recovery perspective, understanding this Layer 6 cryptographic process is vital. Security researchers analyzing Xion had reverse engineered this specific encryption logic, how keys were generated, used, and stored to potentially develop decryption tools. That reverse engineering, figuring out the data transformation and key management scheme, is a deep Layer 6 forensic skill. So while the delivery might be L7, the core damage mechanism and the path to potential recovery lies firmly in understanding or potentially undoing the Layer 6 operations.
That's fascinating. So even common threats like ransomware have a critical Layer 6 component in their actual payload. This has been incredibly insightful. We've really dug into the depths of Layer 6, revealing its hidden importance and, frankly, its hidden dangers. So bringing it all together, what's the single biggest takeaway for organizations listening and for individuals too? How do we move forward and build better readiness against these kinds of threats? What's maybe the first tangible step a security leader should consider after hearing all this?
The biggest takeaway, I think, is the imperative shift from purely reactive security to being genuinely proactive, especially concerning these fundamental layers. Waiting for the L6 exploit to hit is too late. This aligns perfectly with frameworks like NIST CSF focusing on the identify and protect functions first. Understand your L6 exposure, then build defenses. For organizations, this means several key things. Firstly, secure coding practices aren't optional, they're paramount. Train developers specifically on Layer 6 risks format strings, encoding issues, safe handling of cryptographic APIs. Make it part of the culture. Secondly, enforce a strong cryptographic policy. No excuses. Disable old protocols, SSL v3, TLS 1.0, 1.1. Mandate TLS 1.2 minimum, push for 1.3. Use strong ciphers with perfect forward secrecy. Audit these configurations regularly, don't assume they're set correctly. And thirdly, implement secure file handling and input validation robustly. Canonicalize input. Validate file formats carefully before parsing. Use secure libraries for handling complex data structures. Treat all external data as potentially hostile until proven otherwise.
So build security into the foundation. What about that first tangible step for a leader?
I'd say the first step is assessment and awareness. Ask the question, does our team understand Layer 6 risks? Do we know where we rely on complex data parsing, encryption handshakes, or file format handling? Conduct an internal assessment or awareness session focused specifically on these L6 concepts. You can't defend what you don't understand or acknowledge. And looking ahead, the future here is definitely automation with SOR. As threats get more sophisticated, manually chasing every L6 anomaly won't scale. SOR platforms will be key to automatically analyzing things like file entropy, protocol negotiation anomalies, and triggering rapid containment actions. Neglecting the presentation layer just isn't viable anymore. A robust, future-proof security posture has to include a dedicated, tactical focus on Layer 6. It requires that integrated, multi-layered thinking.
We've definitely peeled back the layers today, haven't we? Revealing Layer 6's vital role in making the internet work encryption, compression, translation, but also how cleverly attackers can twist those functions. It's a stark reminder that security isn't just about the big, visible things like firewalls or endpoint protection. It's also deeply embedded in the fundamental ways data is represented and interpreted. The invisible plumbing matters.
Absolutely. So maybe a final thought for everyone listening. The next time you send that encrypted email or browse an HTTPS site or open a PDF, take a moment. Consider that invisible translator, Layer 6, working hard behind the scenes. And then consider the sophisticated attackers who are actively learning to speak its language, looking for those subtle flaws in translation or presentation. What previously overlooked layer, maybe in your own understanding or in your organization's systems, might just be that hidden vulnerability waiting for its moment.
That's a powerful and slightly unsettling question to end on. Definitely food for thought. Thank you for joining us on this deep dive into the presentation layer. Keep learning, stay curious, and let's all work to keep those systems at every layer secure.